Hello and welcome to the CSES problem set meetup today. I just need a confirmation that you can hear me fine because I was talking for a while and I didn't get any response. So I'm not sure whether you can hear me fine or not. All right. Yeah. Thank you. Thank you for the confirmation. So in that case, we'll get started. We have got two problems today. One is called permutations. The other is called number spiral. So these two problems we'll try to solve. There is a lot we can discuss about both the problems, so we'll see how much we can do today. Let's get started with the problem statement. This says a permutation of integers 1 to n is called beautiful if there are no adjacent elements whose difference is 1. We need to arrange them in such a manner that no two elements whose difference is 1 can be together next to each other. So a sequence like this is obviously not beautiful as per this definition. Now, given n construct a beautiful permutation, given n construct a beautiful permutation if such a permutation exists, and if it does not exist, we'll say this no solution. So the input is going to be the only input line. The only input line contains an integer n. We'll just get this number n. Print a beautiful permutation of integers 1 to n. So if a permutation like that exists, we have to go and print that permutation. If there are several solutions, you may print any of them. If there are no solutions, print no solution. This string we have to print. The constraints are given. And here's an example input, here's an example output. So the moment we see this output, we can already get some clues about how we could create a beautiful permutation as per the definition of beautiful given here. We can see that on the left side we have put all the even integers, and since we're putting all the even integers, the difference between them will be 2, which satisfies this requirement that no adjacent elements can have their difference as 1. And here we're putting all the odd numbers. Again, between them the difference would be 2. The only tricky part is to ensure that this difference will be 2, where we are crossing this boundary here, where we are going from even numbers to odd numbers. And that is where I would get into exploring some patterns here and see what kind of patterns emerge, and then we will have, of course there can be multiple possible solutions for something like this. We'll pick one solution that works for all possible cases that we might want to take care of. Let me bring up a board which I had prepared for this. Yes, so here it is. So there are so many possible ways to arrange these numbers by keeping the odd numbers together and the even numbers together on the other side. So for example, here is one possible example. So here we are taking n equals 5, and this also shows all the different cases that we have to think about in our mind. So if you're given an odd n, and here the example is 5, so if you say we are given n equals 5, we could do something like this. So a specific example here, we can keep all the odd numbers in descending order at the beginning, followed by all the even numbers towards the right side. So in general, it would look like this. So n followed by n minus 2, followed by n minus 3, and so on up to 1, and then from n minus 2 up to 2. So these are all the even integers. Now we have to be careful that this difference is at least 2. Here the difference is already guaranteed to be 2 because they are all odd numbers. Here also all the difference between the adjacent numbers are guaranteed to be 2. This is something we have to take care of. It is not guaranteed in a natural way. So the condition here is we want n minus 2 to be at least 3. That is at least a difference of 2. So that's what is written here. So this kind of arrangement will work if n minus 2 is at least 3, which is the same thing as saying that n should be at least 5. So that gives us a constraint. So this strategy works only for n greater than or equal to 5. This strategy will break down if we choose n equals 4. Okay, n equals 4 is not valid for odd n equals 3. Then this strategy breaks down. And why is that? Just imagine what happens if we put 3 here. We'll get 3 and then 1 and then 2. And 1 and 2 are not sufficiently apart from each other. The difference is just 1. So similarly, we can do a lot of analysis like this for each possible case. So let us say we are given odd n, and this time we decide that we want to start with even numbers. We just want to experiment and see what happens if we start putting all the start the sequence with even numbers. In this case, we will have 4, 2, 5, 3, 1. This looks good, but let us see if it breaks down in some smaller values of n. So in general, this would look like this, n minus 2, because we are given an odd number, n, which is 5 in this case, and we are starting with the even numbers. So that would be, okay, have I made a mistake here? N minus 2 is not even there. So I think I made a mistake in preparing this board. Let me just check once again. Okay, we're supposed to start with n minus 1. So I think the mistake I made is here. This should be n minus 1. I'll just keep a note of that and fix that later. And let me see if I can fix this board also now. So we mean n minus 1 here because n in this example, if you see the example, n was 5. Yes, I think I fixed it, but there could be more errors. So just keep a close eye on the board in case you spot any mistakes. So given an odd n, in this case it is 5, and we choose to start with the even integers, this is how the sequence would look: n minus 1 up to 2, and then we put all the odd integers. We start with n up to 1. Again, we have to make sure that this boundary is okay here, and we need n to be at least 4, because n should be at least 2 more than this 2, which is n greater than or equal to 4. And since we are dealing with odd n, that is the same thing as saying that n is greater than or equal to 5. So once again, this strategy works only if n is greater than or equal to 5. It does not work with n equals 3. And we'll have the same problem if we these two numbers will disappear. This number would disappear if we choose n equals 3. So what we'll be left with is 2, 3, and 1, and 2 and 3 are not sufficiently apart from each other, and so on. We can just keep doing this analysis. Say we are given an even n now. We are not. So this was case 1, dealing with odd n, in which we had two subcases. We could either start from the odd number itself, or we could start from the even number. Now this is case 2, and this is subcase 1 of case 2. If you're starting with even n, and we choose to start with that number itself, then it would look like this. In this example, n equals 6. So we put all the even integers first, which is 6, 4, and 2. And we put all the odd integers, which is 5, 3, and 1. In general, this looks like this. We start with n, end with 2, and then again we start with n minus 1. We end with 1. As per the requirement of beautiful permutation, we need this difference to be at least 2. The difference between 2 and n minus 1 should be at least 2, which is the same thing as saying that n minus 1 should be at least 4, which is the same thing as saying that n should be at least 5. We're just adding 1 on both sides of this inequality. And since we know that we are analyzing the case where n is even, n has to be at least 6. So this strategy is even weaker in terms of finding a solution. So this strategy was working for values as low as 5. This strategy is only working for n greater than or equal to 6. Okay, it's not necessarily weaker because we're working on even n, but yeah, that's something to keep in mind. And even n with starting with n minus 1. So we are given 6 as an example here. We could choose to start from the odd integers, the sequence of odd integers here, followed by even integers. This is the general form. We're starting with n minus 1 because we are given an even n. We're starting with odd integers, so n minus 1 all the way up to 1, and then again n all the way up to 2. And we have to keep this difference, at least this difference between n and 1, at least 2, which is the same thing as saying n minus 1 is greater than or equal to 2, which is the same thing as saying n is greater than or equal to 3. And since n is even, that is the same thing as saying n is greater than or equal to 4. Basically, this implies that n is greater than or equal to 4, considering that n is even. So what did we... So from all these cases, what did we learn? We learned that if we start with n, okay, because when we write the code, we probably want to make the code as simple as possible. We don't want to have a case-by-case we don't want the code to have too many if then else. We could do that, and it would be a valid solution, of course. Um, but we want to keep the code as simple as possible, and for that we would want to find a strategy that works for everything that we care about. So here we see that if we start with n itself, so case 1 start with n and case 2 start with n, we see that this only works for n is greater than equal to 5. Okay, so this is n is greater than equal to 5, here is n is greater than equal to 6, but this is even, so we can just say that start with n will work for n is greater than equal to 5. If we start with n minus 1 instead, it works for n greater than equal to 4. So this strategy works a little bit better than this one if you want to write a simple solution. And we can also analyze this in the opposite direction. So if we, whatever holds good in the descending order, so here we are arranging all the numbers in descending order, and whatever holds good here, we can just reverse this arrangement, and the analysis that we have done so far should still hold good. So in the solution that I have implemented, I'll be printing the numbers in ascending order, pretty much this analysis, and I'll probably use something like this. So I have a separate board for that where this is neatly expressed once more. Let me see. Yeah. So here I'm arranging everything in ascending order. Now we'll not go through every case here once more. The analysis is similar. It's just looking at this boundary between n and 2 and making sure that the difference is at least 2. So using that, using a similar case-by-case analysis, let us see what we get. So I will just focus on these conclusions here, like what the strategy, for what kind of constraints the strategy works. So the first strategy, case 1, sub case 1, is we are given an odd n and we start with 1. So there we were thinking about starting with n versus starting with n minus 1. Here we are comparing starting with 1 versus starting with 2 and see what works better to give us a simple solution. So if we start with 1, we get a general form like this, 1 all the way up to n, all these odd integers, here 2 up to n minus 2, all the even integers, and we want this difference to be at least 2, this difference between n and 2, which is the same thing as saying n is greater than equal to 4. Now, if n is greater than equal to 4, that implies n is greater than equal to 5 because we are dealing with odd integer. And now, so I just walk through one case in detail. I'll just skip over the remaining because it's similar to the previous board. Just focus on the conclusion here. If we start with an odd n, if you're given an odd n and we start with 2, say we decide to start with 2, then we are getting this constraint. So we are saying that this strategy works if n is greater than equal to 5. If we start with 1 for even n, this strategy works for n is greater than equal to 6, which is the same thing as n is greater than equal to 5 as well. So we have learned something about the first strategy, which is start with 1. It will work for n is greater than equal to 5. What about the second strategy, which is start with 2? N is greater than equal to 5 here, n is greater than equal to 4 here. So the second strategy works for n is greater than equal to 4. So if you're given an even number with 4, if you're given an odd number, it starts working from 5 itself. So the start with 2 strategy works for n is greater than equal to 4. What about 1, 2, and 3? What about those numbers? So that we can very easily we can verify by inspection that we cannot have a solution for 1, 2, 3. So there is no way to arrange, say, 1, 2, and 3 that we will get 2 adjacent numbers having a difference greater than 2. And in case of the number 2, when we have to arrange just 2 integers, 1 and 2, it's even more obvious. 1 and 2 have a difference of 1. So for n equals 1, n equals 2, and n equals 3, we do not have any solution. So we can just go ahead and print that. For other numbers, if we choose the strategy 2, which is start with 2, it works for all n greater than equal to 4. So we can write our solution with that in mind. And let me show you my solution. And once again, like problems like this do not have a single solution. There could be so many ways. Somebody could choose to implement one strategy for n is greater than equal to 5 and just deal with n equals 4 as a special case. That would be also a valid solution. But I'm just choosing a simple one here using this strategy. So here's the code. If n is 2 or n is 3, I print no solution. Oh yeah, so I forgot n equals 1. So if you have n equals 1, it works because we only have a single integer. And in fact, this strategy also works, start with 2. We will just go ahead and print a single odd number. So it works for n equals 1 as well. For n equals 2, n equals 3 does not work, so no solution. For other n's, what we are doing, we are just following this strategy, start with 2. We're starting with 2, going all the way till n, and we're skipping one number in between every time. So 2, 4, 6, 8, and so on. Here we're starting with 1 and doing the same thing, going 1, 3, 5, and so on up to n. So yes, so that brings us to the end of this problem. I'll just check if there are any comments to be shared. If you have any other interesting approaches to this problem, you can unmute yourself and talk about it, or you can also post it on chat. Yeah, so there's a lot of chat messages. I'm just going through some of the chat messages towards the end. So Charim says there are also solutions that do not insist on even odd separation. Yes, say interleaving 1, 2, 3, and by 2. Yes, of course, there are more solutions possible. And maybe there are problems later that would explore that, because I've seen there are variants of the same problem in this problem set. So it would be nice to explore those things as well. And there's a link from Charim, maybe, yeah, which asks for the exact number. That'll be interesting. So I have not solved that yet. Nazari says this is an interesting analysis. I've just accidentally chose to start with n-1, like in the first example test case. Yes, and that is one of my intentions for doing this. I want to take a look at every problem in a more elaborate manner and see if there are more things to be discovered about that problem. Even though even if I happen to land on the right answer by chance, I still want to explore the other properties about the problem. All right, so I'll continue to the next problem now. The next problem is called spiral. So let me go back to the problem set and choose spiral. Yeah, so this is number spiral. Here again, I have two different perspectives to look at this problem. Before I share that, let us first look at the problem itself, what the problem says. A number spiral is an infinite grid whose upper left square has a number 1. Here are the first 5 layers of the spiral. So 1, 2, 3, 4. So it goes like this. So I have set the frame rate to, so the frame rate set for this meeting is 5 frames per second. So that could be a bit low if I'm moving my mouse pointer. I don't know whether you're able to see a smooth movement, but I'll also read aloud the numbers. So here is how it goes. 1, 2, we went right side, then down, 3, left, 4, then down again, 5, and then right, 6, 7, and we go all the way up to the diagonal. We don't cross the diagonal. And at the diagonal, we change direction. We are again going up. So 7, 8, 9, and then going right, 10, then 11, 12, 13, again to the diagonal. Again, we're going left, 14, 15, 16. So at the diagonal, we change direction. We either go left or we go up in an alternating fashion, and so on. So it's like it's not exactly a typical spiral that we usually see in pictures, but a different kind of spiral. Almost like a snake kind of spiral this is. Now the question here is, your task is to find out the number in row Y and column X. So the notation which I'll be using throughout the board is row, comma, column. So Y, comma, X. This side is Y, so this is Y equals 1, Y equals 2, Y equals 3, Y equals 4, and so on. This side is X, X equals 1, X equals 2, X equals 3. So the notation I'll be using to denote a number would be, to denote the place of a number would be Y, comma, X, row, comma, column. And it is 1 based index, right? I think so. We'll know that from the constraints. Yes, so it is a 1 based index. So the smallest value of Y is 1. The first input line contains an integer t, the number of tests. After this, there are t lines, each containing integers y and x. For each test, print the number in row y and column x. So here it is. Some examples here. So say 2, 3. So what is the number at 2, 3? So row number 2, this is the row number 2, column number 3. So 8 is the number there. So 8 is the expected output. So that is the problem. Let us do some analysis of this problem now. Yes, so all of these boards that I'm sharing and discussing with, these are all available on the website. You can see the URL here of page.cc/CSES boards. So if you just land on offpage.cc, you can find your way into the list of boards, and you're welcome to go through it later, and if you find any mistakes, just let me know. I will fix those mistakes. Okay, so I'll just close these permutation boards. We don't need them. Just the number spiral. So I've drawn the number spiral here once again, and I've shown this dots to show it's an infinite spiral. It keeps growing on all sides, and we may be asked about any number here, given subject to those constraints that are here. But let us just solve it for any number, any position, considering that this spiral is infinite in size. Some notation I've introduced. F, y, comma, x represent, okay, here is an English mistake here. It should be let f, y, comma, x. Oh no, this is correct. I read it wrong. So let f, y, comma, x represent the number in row y and column x. Okay, so y, comma, x. Y is the row, x is the column. Now what happens to top edge? Let us see the top edge. So this is an analysis from the perspective of the edges. Okay, so we'll try to find these numbers by doing some computation with the edges, edge numbers. That is what I'm doing on this board. So f1 comma x, so which is the first row. Okay, so what happens here? We see that all the odd columns, odd numbered columns, has a perfect square. So this is 1, this is 9, this is 25. So that is what I've written here. So f1 comma x is x square if x is odd. As an example, this is column number 3. So 1 comma 3 is the position, the place. 1 comma 3 has 3 square. What about this? What is going on here? So here we just have one more than the previous perfect square. So if you want to find what this number is, this is just one more than the previous perfect square, 9, 10, and that is because of the snake-like pattern in which the spiral is done. So this number at even x, at an even numbered column, the answer would be the previous perfect square plus 1. We learned something about the top edges. So basically we have to find all the numbers in the top edge. A similar analysis for the left side edge. There is no right side or bottom edges because it's an infinite spiral. It just keeps growing in both directions. The only two interesting edges that we have, or the only two edges that we have, are the top edge and the left edge. The left edge is also similar, except that the parity changes here for the y. If you see here, at every even numbered row, we have a perfect square. So this is row number 2, we have 2 square. This is row number 4, we have 4 square. And the same pattern continues. And what about the odd numbered rows? It's similar. So here we take this 4 and add 1, we get the odd numbered row. So that is the formula mentioned here. So f y comma 1, we are dealing with row number y at the first column, which is the left edge. So f y comma 1 equals y square if y is even, y minus 1 whole square plus 1 if y is odd. So that specifies the numbers at the edges. Now we'll understand how in the code we can deduce where we are on, because the way we will use these edges and find our number depends on whether we are on the bottom side of this diagonal. So this is the diagonal 1, 3, 7, 13, 21, whether we are at the bottom area of the diagonal or we are on the top area of the diagonal. So we can call it top or we can call it right side of the diagonal. We can call this bottom or we can call this left side of the diagonal. And the way we do the computation depends on that. So we'll learn how to detect which side of the diagonal we are in right now. So yx, so this is showing that, this section here, yx falls exactly on the diagonal if and only if y equals x. And that is obvious. So for example, let us take this as the example, 7. So this is at position 3, row 3, column 3. So that is y equals 3, x equals 3. That's what this is saying. Yx falls exactly on the diagonal if and only if y equals x. Yx falls above, so I will not use this terminology for now, but I'll just say above and below the diagonal for now, just to keep the language simple. So Yx falls above the diagonal if and only if y is less than x. Okay, so this is something to check and verify and convince yourself. So maybe I can just show an example. So this number is above the diagonal, right? So this number 11 is above the diagonal. So y is 2. x is 4, and indeed y is less than x, 2 is less than 4. That's a quick sanity check on this condition. Similarly, yx falls below the diagonal if and only if y is greater than x. We can just say it is by symmetry, it has to be true, but we can also do one sanity check. So let us pick this 15. 15, y equals 4, x equals 2. So we are seeing that 4 is greater than 2. And we can also, there are ways to argue, like to arrive at this inequality in a slightly more rigorous manner, but I'm not doing that. I think this is clear enough. But if you just stare at it, you can also, by spending some time, you can also figure out why this is so, because at the diagonal we will have y equals x, then we have to go some direction. So depending on the direction, either y or x will become less than the other number, which is x here. So these are the conditions. So we can just check, compare y and x, and we can find out which part of the diagonal we are, which side of the diagonal we are in right now. And depending on which side we are in, and also depending on the parity of the column number or the odd number, we have to do some calculations. And that is now what we will see. So what is this number, f1, x? Okay, let us see this one. So this is saying that if the number is above the diagonal, so this is that condition. If it is above the diagonal and we are at an odd numbered column, okay, so let us check such a thing. So these numbers are some examples of that. So these numbers 24, 25, they are above the diagonal. In fact, 23, all these numbers 22, 23, 24, 25, these are all above the diagonal, and these are also on an odd numbered column, that is x is odd. So what do we do to get these numbers? We have to take this edge number, which is f1 of x, which we know how to compute, f1 of x. We take that number and we see, let us for this example pick 22 as the example. Okay, so we see this place, how far this place is from this top edge, and that we can find by subtracting this value of y from this value of y. So in this case, this value of y is 4. This is y equals 4. This is the fourth row. This is the first row, and that is how we know that the difference between this and this is 3, or we can say the distance between this row and this row is 3, and then we just subtract that 3 from 25 because the numbers are decreasing in this column. So that is the first rule encoded here. We find the top edge number, which is by this formula, and then we subtract the difference because the numbers are decreasing here. And similarly for the other things, when here also we are above the diagonal, but we are on an even number row, and what happens in even number row, the numbers are growing. They're not decreasing, they're growing, and that is because of the snake-like pattern of the spiral. So we add the difference here, y minus 1. And similarly, if you're below the diagonal, then we have to consider the left edges, because below the diagonal, the numbers are growing or decreasing horizontally, not vertically. If you see above the diagonal, the numbers are growing or decreasing vertically, but below the diagonal, they are growing or decreasing horizontally, and we have a similar analysis. So here we take the left edge, which is fy comma 1, and that we can compute. We know how to compute that, plus x minus 1. So this is the distance of the column x from the first column. So that number we add if x is odd. So if we are at an odd numbered row, these numbers keep increasing. So that is why this plus. And similarly for even number rows, we have a negative sign here. So with this formula, we have completely specified the method to compute the number at any cell given the coordinates of that cell. And that would be the code, and the code itself can be written in multiple ways. I just wrote it in 2 different ways to show some variety there. So let me see if I have that problem open here. I think I have it. Yes. So y is less than or equal to x on or above diagonals. We'll just show one condition here. We'll compute the edge first. And how are we computing edge? According to what we're doing here, this is which edge? If y is less than or equal to x, which means we are we are above the diagonal, which means we want to compute the top edge. So this should be a top edge. So this top edge is computed based on the parity of x, which you can see here. If x is odd, we have one formula. If x is even, we have a different formula. we're checking the parity of x and putting the formula x square or x minus 1 whole square plus 1. Then I'm computing the sign, which is whether we have to grow or we have to increase or decrease. So this minus or plus sign, and that depends on the parity of x again, as we can see here. So depending on the parity of x, I'm putting the minus sign or the plus sign from here, and the distance is y minus 1. And similarly for below the diagonal, using the other set of formulas, and the final answer is edge plus sign times distance. So that's one way to write the solution. Now this is not the way I actually wrote the solution. So when I did it for the first time, I had a more raw and intuitive way of thinking, just looking at the patterns and just making a very raw encoding of my thoughts, and that looked something like this. So this code I wrote after doing this analysis. So this is I think a much neater analysis than a raw intuitive thinking. So once I got this formula, I thought I should also code this just so that it is present in the form of code. But the first solution that I had written looked like this. Yeah, so this was like a direct coding of my thoughts. So, and this also is it ultimately is equivalent to what we have done in the previous solution. It just does not look as descriptive as the previous solution, but I think I can show it very quickly that it is exactly the same thing. Let's see here what is happening here. If you're on or above the diagonal, then x mod 2, we are checking the parity of x, and if x is odd, so this value, this value is, this whole formula is written in one line here, and if x is odd, we choose x square, right, minus y plus 1, because if x is odd, we also have minus y here, minus sign here, which makes this whole thing minus y plus 1. And if x is even, then we pick x minus 1 square plus 1, and then we put this formula, and that 1 and 1, they cancel each other, and we are left with just y. It looks like this. So I'm just showing that it is equivalent to what the analysis that we have done here, but that's not really how I coded. I just literally looked at this picture here, this diagram here, and see what kind of computation I need to do, and just encoded that directly here. But it's the same thing. It's just that I think this kind of analysis is easier to explain. It's slightly more rigorous than an intuitive visual understanding of this spiral. Okay. So this is where we will stop then, because I do have another analysis, and I'll just give a quick intro, and you can see this board later. All these boards are shared. So this is the last board for number spiral. If you just go to CSES, our club website, which is offbeat.cc.cscs, and if you just go to these boards, meeting notes, new board files, and if you go number spiral, the second example, here I have done an analysis using the diagonals as the reference point. So here, so in earlier analysis, I was using the top edge and the left edge, and then adding or subtracting something. Here I'm computing the diagonals instead. So I have a formula for the diagonals, and then I'm adding or subtracting something depending on the parity of x or y, and where we are on the board, whether we are above the diagonal or below the diagonal, based on that. But that will not fit in 4 minutes. So we'll continue with this tomorrow, along with reading the book. So tomorrow we have a book reading session. We'll first complete this analysis and then continue with the book. But since I've done the first analysis in a very elaborate manner, this board should make sense. It should make a lot of sense. We'll see this tomorrow. Let me now go back to, so one nice thing about this is that after filtering everything, after distilling the whole analysis, it just comes down to a single formula, a very neat formula. And I can show you the code as well. Okay, this is too descriptive. I think I had a smaller thing somewhere. Yes. So this single formula is encoded as a single line of code. So the whole problem can be expressed, the whole solution can be expressed as almost at least the essence, not the whole solution, but the essence of the solution can be expressed as a single line of code because of the analysis that is done on this board. And that is something we'll see tomorrow. Okay, I will now just quickly show the schedule where we are at. So let me go back to the club main page, not this. I'll just cut this URL. We have the meeting log here. Yes, so we were supposed to finish permutations in number spiral. We did half of the analysis, or we did one complete analysis. I'll do one more analysis tomorrow using the diagonal, and then we'll read the competitive programmer's handbook. We'll try to complete at least the first 10 pages tomorrow. That's the plan for tomorrow. And this is where we stop. I'll just give it a couple of maybe 1 minute to just see if there are any more comments to be shared about what we have studied so far. Jai says amazing analysis of this problem. Susan, thank you. You're welcome, and thank you for joining the sessions. Okay, there are no more chat messages. In that case, I think we are good to end the session now. We will meet again tomorrow. It is same time, 1700 UTC. The plan for tomorrow is to look at the number spiral problem a little bit more and then read the handbook that comes with this website. That is all for today. Thank you all for joining. See you again tomorrow. Until then, take care and goodbye.